This is the first video on section 5.2, limits and continuity of functions of several variables. And I didn't write the whole title up here because I didn't have room. And so, first of all, we're going to look at a couple of definitions. Definition 123, we're going to look at what we call the norm of x, where x is an Rn. So we square each coordinate of x, add those together, take the square root. This looks a lot like the magnitude of a vector, and it is. So remember, when we calculate the magnitude of a vector, we square the components, add them together, take the square root. It's the same operation, except we're doing it on a point in Rn instead of a vector in V sub n. The distance between 2 points in Rn is, we take the difference of each coordinate, square those, add them together, and take the square root. This is how we measure the distance between 2 points in Rn. Definition 125, along with notation 126, we have the ball about x of radius epsilon. That's what this is. It is simply the set of points in Rn whose distances from x are less than epsilon. So we're looking at the set of all points that are close to x. Now, in R2, this is a circle. This is a circle centered at x of radius epsilon. It's the interior of the circle. We don't count the points on the edge because it's strictly less than. In R3, it's a sphere. Set of all points that are less than some distance from a given point. So it's the set of all points that are inside the sphere but not on the sphere. And in R1, it's an interval. So what I want to say about that is, if you think about R1, so just some point in the real line, this is simply the absolute value of x. This is the absolute value of x minus y. So what we call distance here, if we apply this to R1, is the same thing we've been calling distance all along. That's a good thing to keep in mind when I give you the definition of limit, and this theorem is an equivalent definition. What I want to say at this point is limits in Calc 3 are not always this scary. So when we looked at limits in Calc 1, we had the epsilon delta definition of limit, then we had some other techniques of calculating limits. Same thing happens in Calc 3. We're going to start with an epsilon delta definition of limit, but then we're going to learn some other techniques for calculating limits, and they're basically three-dimensional versions of what you learned in Calc 1. So what I want you to realize is limits are not always this intimidating. So in the next video, we'll calculate some limits that are not too difficult. But what is our definition? We have a function from Rn into R. We have a point in Rn, may or may not be in the domain of f, just like in Calc 1, and then we have a real number L. That's what we have up here. What does it mean to say the limit as x approaches c if f of x is L? Now remember, x is a variable in Rn, c is a number in Rn, and L is a real number. So for all epsilon greater than 0, there's a delta greater than 0, such that what happens? Well, the distance between f of x and L is small. So it's less than epsilon whenever the distance between x and c is small, but x is not equal to c. Okay? Let me elaborate on that x not equal to c for a moment. That doesn't mean that x isn't allowed to be c, and it also doesn't mean that f of c minus L isn't allowed to be less than epsilon. Okay? What it means is we don't care if it is. So we don't care if f is defined at c or not, and we don't care what its function value is. That doesn't mean that c is not in the domain of f. It simply means we don't care if it is. It doesn't mean that f of c isn't nice. It's just that we don't care if it is. Just like, remember back in Calc 1. Sometimes f of c wasn't defined, sometimes it was, but you had the graph of a function and your f of c was clear up here. You had a jump discontinuity, and that didn't affect the limit. So it's the same thing here. We don't care what f does at c. We care about what happens when x is close to c. And this is what we mean by x being close to c in this context. An equivalent way of saying that is, okay, for all epsilon greater than 0, there's a delta greater than 0, such that what? This distance is again small whenever this distance is small but greater than 0. Again, we're not saying that x cannot be c. We're not saying that this distance is never 0. We're saying we don't care what happens when it is. So as long as x is not equal to c, we want this to happen. When x is equal to c, we don't care what happens. That's what we mean when we're insisting that x not be equal to c. And again, think back to Calc 1. If this were a function from R1 into R, this is exactly what we were saying in Calc 1, because this distance right here that we're calling the distance between x and c is the absolute value of x minus c in R1. And these balls right here, these were just intervals in Calc 1 because we were just working in R1. So first of all, what we're doing here is the n-dimensional version of what we did in Calc 1. Our techniques of taking limits are going to, in a similar way, be n-dimensional techniques of what we learned in Calc 1.